All right. Good morning, afternoon, or evening, everybody. This is your host, Jennifer Brennan. I'd like to welcome all of you to the Laser Altimetry Applications for a Changing World, working with ICESat-2 Inland Surface Water Data Training Webinar. Today's event is the fifth event in a multi-part series of ICESat-2 specific data training webinars. It is 2 p.m. Eastern Time, so what I'll do first is just begin today's event with a few logistics. To ensure the best audio experience, all participants have been placed in silent mode. But if you have any issues or you have any questions, please enter them into the Q&A panel, and you can find that located on the right side of your screen. If you don't see that, you can click on the three dots at the bottom of your bottom right corner to pull up your panel options and insert a check mark next to the Q&A. Or for some of you, depending on whether you're on a browser or the desktop application, it might look like a really tiny floating question mark, okay, at the bottom of your screen. Today's webinar is being recorded. The recording will be posted to the NASA Earth YouTube channel within a week of completion. And what I will do on my end is once it's completed, I will send an email to all registrants and participants, that includes links to both the recording and presentation slide decks used within today's webinar. As far as timing is concerned, today's event will be 1 hour and 30 minutes long, with 1 hour or so dedicated to the presentation and live demonstration, and a 15-minute question-answer period to begin after the presentation. Depending on the volume of questions received, we may extend the Q&A session, but we will have a hard cutoff of 3:30 p.m. Eastern Time. During today's webinar, we have three speakers. Our first speaker is Dr. Amy Neely. And with that, let me actually advance that slide here. Amy is the ICESat-2 Mission Applications Lead here at NASA Goddard Space Flight Center. She will provide you with some information regarding the ICESat-2 Data Training multi-part webinar series and today's event. After that, we will transition to our second speaker for this afternoon, Dr. Michael Kozinski. Dr. Kozinski is a research hydrologist at NASA's Goddard Space Flight Center. He will provide an introduction to both the ICESat-2 ATL13 and ATL22 Inland Surface Water products and measurements. And then from there, we are going to transition. Kozinski, yes, I see I've made an error. I'm so sorry about that, Michael. I'll make a correction here. From there, we will transition to our third speaker this afternoon, Dr. Jessica Issyk. Jessica is a research assistant professor at the University of New Hampshire. She will provide an introduction to icepyx and provide a Jupyter Notebook tutorial and data workflow that showcases the use of ATL13 for Lake Mead. After she is finished with her demonstration, we will transition to our final optional polls and then move directly to the question and answer period. Before I toss it over to Amy, though, I do want to cover one final note about the Q&A session and also the chat. We will try to answer all questions within the time allotted, but if we're not able to address your question during the Q&A period, our speakers will be able to follow up with you offline. And then regarding the chat is viewable only to the hosts and panelists. And so if you have some information you'd like to share with other participants, please do enter that into the Q&A panel. And so with that, it is my pleasure to introduce today's first speaker, Dr. Amy Neely. Amy, and with that, let me stop sharing my screen here, and I am going to toss it over to you. I'm so sorry about the misspeaking with Michael.
Okay. So my job here is to just provide a brief overview of this data training series. So we've had multiple one of these. This is actually the fifth of the training series that we've been hosting, and I'll show you the different ones in a second. But we had several motivations for putting these webinars together. The first is to highlight the capabilities of ICESat-2 and its data products, which expands beyond the cryosphere. To build capacity, show the community what tools exist and the accessibility of these data so that they can use these in their research. And lastly, we want to grow the community. We want more people to know these data exist, know that they can use these data so that they can be explored and new applications can be developed. So during these webinars, we typically have three parts, or three components, I should say. The first is a data product overview, which Mike will provide. He's going to talk about the ATL13 data products in detail. And then we'll have, and he'll also discuss some use cases. And then Jessica is going to provide that wonderful live tutorial of icepyx, which will also include a short use case as well. So you'll get a nice understanding of ATL13 and a great tool you can use to access it. So I mentioned that this is actually the fifth. So we've had four since we started actually this month last year. We've had one on sea ice. We've had one on the new bathymetry product, ATL24. It's a coastal bathymetry, shallow water bathymetry product. We've had one on forest vegetation and an introductory one at the beginning where we covered ICESat-2 and also gave an overview of OpenAltimetry, which is another tool or resource you can use to access and visualize data. And we'll have those links available for you all if you want to browse these. They've all been recorded. They're all on YouTube, so they're available for you to access. And lastly, I like to throw this slide in just to show how many different tools and resources we have. First, the ICESat-2 website, and then we have, the NSIDC, which is the data repository. For ICESat-2, we have cloud computing, we have GUIs, we have Python notebooks. There's so many amazing things that have been created by very smart people to make this a lot easier for the rest of us. So I would highly recommend, especially if you're interested in other products or interested in different tools, I would recommend you explore these options. And that's it for me. So I'm actually going to stop sharing and toss it to Mike so he can talk about ATL13.
Okay, thank you, Amy. Jennifer, Jessica, Amy, for putting this together. I greatly appreciate this opportunity to present in front of this larger group of applied science users. So to start, we actually started developing this product before the launch, which was in September of 2018, using prototype data, very high altitude Mabel sensor. And many of the algorithms were developed for that sensor, ready to go as soon as after the launch of ICESat-2, and once it was ready to go. Okay, so the team here, the core team of we've had a lot of team members in the beginning and come in and go out, but the real core people who have been with us since the beginning are, besides myself, Jeremy Stoll in our lab, David Hancock and John Robbins. They provided us, helped us with the theory, and we've had other folks along the line, either programmers or advisors like Jyoti, Natala, and Claudia Carvajal to help us along the way. I myself, I'm a hydrologist, and I come from a civil engineering background, and I worked as a hydrologist in the field as a water resource engineer prior to coming to NASA. And it's really exciting to take this instrument and try to obtain parameters that water resources engineers and users can use. And basically, for the most part, in this type of environment, we're looking at physical hydrology. We're not looking at the interactions with the carbon cycle. Well, we're looking at sort of standard applications for stream flow, flooding, penetration of light into the water, and a lot of hydraulic parameters that can be applied, can be derived using ICESat-2. Okay, so let's get going. So what is our domain? The domain that we created for this product is global, and it's shown here for just North America, but it's a global domain. Everything in blue and yellow is contained in a water mask, a single water mask that is derived from, on the right-hand side, lakes and reservoirs from Messager and all from 2018. He had 2016 and later 2018. He had a set of lakes from hundreds of square kilometers to lakes as down as small as 0.1 square kilometers, and well distributed on a Pareto curve. And we were able to include each of those lakes in this mask, merge it into one file. And I just have some. So that's the main area of interest that we're targeting. But we're also targeting rivers, the coastal water, and estuaries. For the lakes over here, I just want to highlight. If you look on the left-hand side, there's a red call-out box up in the north part of Alaska, and in that lake alone, in that region alone, there's 30,000 lakes of just greater than 0.1 kilometers squared, and it's really that way across the Panarctic, across northern Canada as well. For rivers, there was no river mask, but we created a river mask using Allen and Pavelski's RivWidth database back in 2018. And since lakes expand and contract based on season, drying, and wetting, we developed a flexible mask, a mask where we had a buffer that we would take this structure that we have in front of us here, but we would buffer it and then test using the satellite. We would test whether it is inside actual water, not just whether it's inside the mask. And that helped us to move forward quite a bit with getting fairly good estimates of the lake crossing distance, as well as the altimetry, the height of the water body that we're looking at. And we have a paper actually out on that's in review, that flexibility of the mask. Coastal water, we had a hint based on the Mabel data, that is the prototype data, that we were going to get bathymetry. So we added a buffer to the coastal zone. And you can see there's a call out on the right-hand side with the buffer. And it's sort of focused on the Chesapeake Bay off the east coast here of the United States. So that sort of yellow strip there is all buffered just 7 kilometers out. If the bathymetry is achievable, we'll look in that area to find out if it does exist. So we also used a database of named marine water bodies from Esri, and that just helped make the conversion from sort of the true estuary zone up to the rivers where we have better data. So this is our product domain, and we have the same type of domain for all the continents. Okay. So what is our product? So our inland water products are summarized right here in these 3 schematics. On the left-hand side, we just start with the satellite observations. For folks who don't know how ICESat-2 works, ICESat has 6 beams divided into 3 pairs of beams, as shown on the left-hand side. And as ICESat moves along, it has an incredibly high pulse rate, about 10,000 kilohertz per second. And what that does is, despite its fast speed going around the Earth, it only advances 70 centimeters, that is 0.77 meters here, as it's progressing along the land. So you get a lot of overlap of the shots. The actual retrieval area is about 11 meter footprint. So, and every photon that reflects off that area directly back into the satellite detector, all the photons are counted and timed so that we can estimate the elevation. And this elevation estimation occurs way upstream of what we do. We take the georeference products and make them into physical processes. Whereas the folks in the project office, they focus right on getting high accuracy geophysical locations of each photon that comes back into the satellite. So we have also on the left-hand side, we have what we call weak beams and strong beams. They just fire less photons for a weak beam that is really designed for going over ice. When you have a highly reflective surface, you don't need as many photons hitting it to get a good retrieval of the characteristics of the surface. But in the strong beam, these are more intended for darker surfaces, water, where you don't have a highly specular return back to the satellite. You can have sufficient photons so that you can make the observation. So in the middle, we have a model. And this model is a development. You'll see some more of this later. But in the upshot of this is that we have a long track product, ATL13, that in segments of 200 photons, we will estimate the parameters in that short segment. And sometimes we get a lot of photons in there, sometimes we get a few. But we have determined that 100 photons per second gives us the information we need to compute the hydrologic and the hydraulic parameters. And at the same time, more appropriate for perhaps water resources is the ATL22. So it's a second product built on ATL13 in which we estimate the mean products for that crossing. So if you want a reservoir elevation and you're an engineer and you're trying to figure out, what's the storage in your reservoir, you don't have to add up, all the way across the lake and deal with cloud cover and all this. We compute directly a mean transect elevation along with the other properties, and that's ATL22. So that's the mean. They're built on the ATL13 short segments. The principal hydrology product, there are dozens and dozens of products that come out of this intermediate products, but the principal hydrology products are the water surface height in both orthometric and lost the word. And with respect to the ellipsoid and respect to the geoid products. So the orthometric products would be the EGM 2008, and the orthometric products would be the WGS 84. And I'm going backwards. Sorry. As you see here on the slide, we have both orthometric and geodetic reference datums for these products. And for water, especially for hydrologists, we want to use the orthometric products. That's what you see. That's what you measure when you're out in the field. And you see the water surface height. That's what we go after. We also compute the subsurface attenuation, photons that go down into the water. We estimate the segment slope, a long track, and we estimate from the slope, we get a surface water standard deviation from which we can estimate the surface water height. And in some cases, when the water is clear, we can get water depth down to about 20 meters. But that's for inland water, which is usually rather turbid compared to like a coastal zone. It's a little more difficult. And I have some examples of that. Okay, and all this information that we have right here in this snapshot is in this document, ATL13, the algorithm theoretical basis documents. It's online, easy to obtain. The most recent edition came out in just August of this past year, version 7. So this citation the work was actually done. Our algorithms are actually computed in 24, but it was just recently the other algorithms had to catch up to ours, and so everything is now published, and it's really a wonderful location. We have version 7 out there as of August, and you can go directly to NSIDC right now and download those data. Okay, enough on that. Okay, so I've put in a couple examples of how we have used these data. And the first example right here is our classic example, and I apologize that people have seen it before, is a flight over Eagle Lake, California on October 19th of 2018. And you can see here, Eagle Lake is sort of just north of San Francisco. The lake itself is not that big. It's just around 15 kilometers by about 10 kilometers. And we flew this transect, and I'm reporting on one transect, a strong beam transect, of the 6 possible transects that went across that lake. And this sort of shows more in a picturesque way what we're actually computing. So first of all, for those who aren't familiar of how ICESat-2 works, I'm going to kind of belabor this and all the details, but the green dots on here are the photons that have returned to the satellite. So you can just imagine this water body is 10 kilometers across, and we have footprints of 11 meters, but with a firing of there's a pulse every 77 centimeters. And from this vast information, we get this beautiful picture of what the cross-section of the lake is. And all those photons along the top, those green photons, that's the water surface. And as you go down to the subsurface, you may only have 5% or less of the photons that actually hit the surface and don't make it any further. But you can see there's enough definition here crossing this lake that we're able to identify the bathymetry through our algorithms, which are semi-empirical, and estimate the bathymetry depth. So along the top, that blue line, kind of a little bit jagged blue line, for each of those little segments, the short segments, we estimate, as I showed in the previous slide, the water surface height, the wave height, the wind speed, and one can estimate the slope. And for the photons that go into the water, we estimate the subsurface attenuation of the beam and the bottom bathymetry. The reason the bottom bathymetry appears to be floating here, the green photons have not been calibrated for the speed of light in water. So we make an estimate of the speed of light, sort of the refraction effect of water on the photon, and that, since light is slower in water, that raises the actual bathymetry. If you threw a rock overboard or the string on it, you would hit the bottom where the orange short segments are. Okay, let's keep moving. So here's another example. This is Lake Issyk over in southwestern Asia. One of the most popular lakes studied internationally. It's a very large lake. It's something like 100 kilometers by 60 kilometers in area, in length and width. Looks like a kidney. And we had this crossing on August 24th, 2021. And what I'm just showing here is what the product looks like as it goes sort of in 3 dimensions. So these 3 sets of little circles here, they represent our estimation of the short segment at that part in that portion of the lake. And so this whole transect here, green, is the right hand beam. This is a descending beam, and it reflects also these green dots here. And you can see just from the cross section, now in this case, the photons we've colored in blue, but we have a water surface with a full suite of ICESat-2 inland water products developed for this surface. And you can see, I don't have the bathymetry in here because the bathymetry comes out of another segment of our algorithm. It's not easily plotted. This was done within OpenAltimetry that doesn't contain the bathymetry. but you can see that there is bathymetry along the shore, stretching a few kilometers in, but at depths maybe only going to about 10 or 15 meters. So the yellow dots represent the pair, but those have less energy, so we don't get as many samples from the weak beam. Now, something to show here is really important when using OpenAltimetry is up here in the top left, there's this red arrow. A really handy thing that the developers used was to put it, they couldn't put all the data here on this page, right? So they sample the data, and the view that we're seeing here of this cross-section only represents 3% in this particular case of the photons and the data product that's being used in this cross-section. And I think that's the case for the photons too in the water. So the blue represents only 3% of the photons that would actually occur in this that we would see for a particular cross-section. Okay, moving. So this is a good result. You can see that we end it. We've correctly identified the edge of the water. The mass goes way outside this lake. It's probably buffered several kilometers out. But through looking at anomalies at the shore, we are able to say, okay, you've reached the shoreline. And sometimes we get a half of our pixel, quote unquote, or a full pixel, but usually we can get within the shoreline, 30 to 50 meters. It really depends on the case. But it's, sort of hard to identify the shoreline. We do it basically based on looking at the altimetry, and we see a big anomaly in the height. We know that pixel needs to be divided up further. That's what we do. The first pixel that doesn't look good, it's like bumped out of place, we start to divide it until we get the correct width. All right. So here's another case, example 3 of looking at a confluence at the confluence of the Koyukuk and the Yukon rivers in Alaska, here in western Alaska. And so it's sort of really far from anywhere. Fairbanks is way over here, and the Yukon is this river here, this sort of this green line, but the Koyukuk comes down from the north, as you can see in the picture. And what's cool about this is we had a crossing of all 3 beams of this river, separated each of those pairs of beams by 3 kilometers, right? So we got the elevations here. And if I start at the left, the lowest part of the river, we have an elevation of 40.99 meters. And then all the way to the cross, we have 41.41 meters. So I just took these elevations and transferred them over here to this little plot. And one can see that between the first, so the river is coming in from the right, going down. So this is the Yukon, and this is the Koyukuk right here. And there's an elevation difference between the 3 of about 0.4 meters. So just taking the elevation change divided by the distance, we get a slope. And we can do this every time we cross a river. So this is a very handy thing. We don't compute this in our algorithm, but it's easily computed from ATL13. Okay, and a final example here is how well do we do in estimating bathymetry in a clear zone? And so we peeked ahead before the product came out because this was one of our test cases. But we have the bathymetry of the latest version of version 7 of ATL13 for the coastal zone. It turns out to be the very last island in the Florida Keys. Okay, so it's called Marquesas, and it was crossed in October of 2019. Now, one thing I got to say here, I'm going to interrupt and say that every time we come out with a new version, okay, so ICESat about once a year will produce a new version. People get to update their algorithms. The data product gets refined a little bit. The original baseline photons that we use get adjusted, or we have different flags or eliminated. And so the algorithms get updated, and each update is a version. So So we're now in version 7, and it's been about 7 years since the ICESat-2 was launched. So you can see, excuse me, on this rising track, excuse me, we have ICESat passing, going up into Florida. It might miss it here, I don't know. But then it would go into Texas or Louisiana. But right here over the Marquesas Island, these are where the 3 beams are. So this is 6 kilometers across. And as you start from the beginning, okay, from west going east, you can start finding the island even before it sort of surfaces, right? And so we were able to identify this bottom using our algorithm, develop the full suite of products for this yellow line, and then all these red short segments are the bathymetry hits. And as you get closer to the island, the elevation goes up, sort of wondering what's happening here. This could be land. This could be cloud cover. We get the full suite. Well, this must be water because we have the full suite of products here. We don't have any products here. So we're approaching land. And finally, with this last beam, the orange dots, the orange pixels, we have the island. So we sort of have 3 estimates of the underwater bathymetry next to this island. And this is about as well as we can do. There's another product out there, ATL24, that was just sort of developed in the past 2 to 3 years, really is a beautiful product. And if you want to do global bathymetry, I recommend highly that you do go to the ATL24 product. But our product within ATL13, it also works pretty good, but they've got so many bells and whistles, and they do an ensemble average of different algorithms, and it's really good work. So, but we have a decent bathymetry algorithm too, using what we had available to us when we were developing it. Okay, so what do we have? What does inland water really offer? We have 3 sets of products. First, we have the long track product, the short segments. They're the baseline. We do all of our analysis right here on ATL13. It's a level 3A product, a long track product. When you cross a water body, you get the full suite of available water surface products in ATL13. That's where like 90% of our work goes. Also, it turns out, and this was sort of a surprise to us, that the product usually comes out about 40 days after the overpass. And that's mainly due to a georeferencing of the data. But they already have a very good estimate of where that data is, within a few meters of where that photon actually landed. Not vertically, but horizontally. And so what for folks in water resources who want like a really quick estimate of the stream flow, you can go to this water data quick look, ATL13QL, and for 40 days, that product will be out there that one might want to use in their analysis, and whether it's a simulation or just looking at some flooding or something. So this is a pretty handy product, and you'll see it has a pretty good user base. In addition, we have the mean product that I showed in the schematic earlier, ATL22. Take all the data across the transect, across the slice of shapefile you've divided up your lake into, or you divided up your coastal area in, and it will give you the averages of the water products. Okay, so metrics. So how well are we doing? Well, in part, we gauge how well we're doing compared to the number of users. And so right now, I've listed the suite of geophysical products here, starting with land ice, vegetation height, et cetera, et cetera, et cetera. ATL13, we're right here, the water surface height. And then below us, we have the quick look products. And you can see, and not ashamedly putting these in red highlight, we're doing fairly well. And in some cases we're doing even slightly better than some of the official geophysical products for which the product for which ICESat-2 was designed. And I think it's because people live on the land. So that, there's a lot of water resources engineers, scientists like yourselves who are listening in, who are most familiar with, hydrology models, HEC models, river forecast system, the National Weather Service river forecast systems. There's so many hydrology models out there, but these products, some of the variables that we produce can be used in these products. And most of the focus is really on reservoir height because that's like the most obvious and the least dynamic of the hydrology variables. So there's a lot of hits on that. And here are the mean products, ATL22. Also, we're sort of holding our own here. There's a lot of interest in using the mean products. And if you're a working sort of hydrologist or operating in a reservoir, you really want to know what the mean height of that reservoir is. And because of the winds blowing and the waves are high, it's better to just get a mean estimate than trying to say, well, this staff gauge sitting at this edge of the lake, this may not reflect, it's way up at the other end of the lake where the water's coming in. So the mean height is often a more practical variable to use. Okay, now I've grabbed some other applications from other folks just to show here. And here's an example of Huilan Gao. She was out of Texas A&M. She's an early adopter. One of the first to really dig her teeth into looking at the data, even starting with the Mabel data. And she's written several papers. Folks are probably, maybe many of you already know her. I mean, she's very active in AGU. But Huilan Gao at Texas A&M has developed a bathymetry approach for reservoirs, and actually it can be applied to lakes. But it's a technique where on the left-hand side, without going into details, so the black lines are the ICESat crossings for one event. But by looking at the area of the lake and the elevation of the lake, she is able to, over time, develop what the bathymetry of that lake would be over the dynamic range. So she's done this, and this is already an old paper. This came out in 2020. I think she may have finished it by now, but this is the only one I could find published. And these so all these red dots are the lakes that she has analyzed the bathymetry of, and these are located at the Texas Data Repository. And her citation of this work is down here below. So another great example of how data can be used is in the assimilation of the altimetry using this data assimilation, combining different altimeters. So this is not assimilating into a model. This is assimilating the data products using not only ICESat-2, but Cryosat, Sentinel-6, and SWAT. And they're different sensors. There's SAR sensors in here, there's radar, and there's LiDAR. Each all have different footprints. But you can see that these time series here are basically of the JSON sensors, the SAR sensors, and the organization that does this is DAAC. It's the German Geodetic Research Institute, and we took some ICESat-2 data and plotted on this this time series that they produced, and we're right in the middle. So I think we did pretty good. So they are assimilating our data. They're actively taking the observations of the lakes when they occur and putting this into their product. And so we're pretty happy that they're using it. Okay, so I'm sort of coming to the end here. Just a summary. So what are the strengths? So the strengths of the data, definitely it offers a global data product, right? At 92 degrees, basically you get the whole Earth. And we are addressing the 1.4 million water body shapes developed from Messinger et al., Leonard Dole, and they have done the hard work in getting the location and the areas of those lakes and doing a histogram of the lakes. And so between those lakes, most of the shapes that we have here are lakes, okay, down to 0.1 kilometer squared. But we've added in the river shapes. We created those ourselves, and the coastal shapes. And but so we get these globally. So that's a plus, okay. Of course, I'm going to show the pluses first. Then the ICESat-2 has extremely high vertical and spatial accuracy. Like where does that footprint land? We're right there on top of it. And the surface height root mean squared error reported for ATL13, which has improved, is 5 to 10 centimeters vertical accuracy. And of course, I said it's for water bodies and rivers of about 0.1 kilometers squared. It also, as I mentioned, we have a crossing width which is less than 50 meters, which allows estimates of long track elevations, even in interrupted lakes. So we have a lake, very dendritic. We go over some peninsula that's sticking out into the lake. We stop making an estimate. We go in, once we hit the water again, we start continuing the estimate of that water. And then we get a mean, we just take the mean of the pixels that are over the water. And we can get a yield of shallow water up to about 20 meters when we have clear water. So these are all pluses. So what is ATL13 and 22? They're well suited for ATL13, probably more like on the hydrology side, where it's more a scientific analysis, but also can be used for hydraulic geometry as stream discharge. On the ATL22, maybe more suitable for water resources applications, especially reservoirs, lakes, water balance, this type of stuff. And it'd be easier to use. And also, we're greatly fortunate that the project has developed many types of software, such as OpenAltimetry and icepyx, which you will see in the subsequent discussion here, that allows folks like me who don't develop software to analyze things, really make it easy for us to go ahead and do our work. Now, the limitations are that there's a low repeat pass frequency analysis, especially for smaller water bodies. It's smaller to hit. We have a footprint of 11 meters. And so we really give up a lot for that, right? But what we have in accuracy, we don't really cover spatially very well. I mean, because we're not like a SWAT mission, we're not like a Landsat mission or PACE mission where you just get these long swaths of covered area when the satellite goes over, and there's nothing we can do about that. However, routine off-pointing targets can be requested. I don't know if they're still doing that, but we did that a lot over Africa on another project, and we tried to hit some of these small ponds in sort of in the Sahel region, and limited to partly cloudy or better conditions. We're also limited due to occasional saturation effects in product development. There actually occur some cases where we have so many photons coming into the surface in a small area, the detector can't handle that, and it's sort of just so we can't really make an estimate of what actually came down. That occurs rarely, I mean, for the amount of data we go through. Okay, so that's it I have for presentation. I again want to thank you folks for attending, but thanks for the people over in the ICESat-2 office for setting us up with these data. ICESat-2, the inland water was not envisioned as a product, and we lobbied for it. We wrote proposals for it early on, and we were able to get it accepted, and we're very grateful to the ICESat-2 mission for doing that and making a product available to the engineers and scientists. And thanks to the folks who have, Jennifer, Amy, Michaela, and Jessica for setting all this up and allow us to have this seminar today. Sure, I haven't answered all your questions. We'd be glad to take more questions even now or afterward. If anyone here would like to contact me further, I'd be eager to talk to you or possibly work with you if you would like. Thank you.
All right. Thank you, Dr. Jasinski. So at this point, we are going to transition over to Jessica. So Jessica, I'll toss you the presenter role, and she will continue forward with an icepyx demonstration and use case.
Thank you, Jennifer. Okay. All set? Looks good. Awesome. Thank you so much. Thanks, Mike, for that great overview of all the hydrology products from ICESat-2. And now we're going to dive more into some technical pieces around how do you get and work with some of this data. And I'm going to showcase in particular something called icepyx, which we can use for data access and analysis. And Mike talked and showed a little bit about OpenAltimetry, which is a great way to explore data in a web browser. It's got a graphical user interface, but sometimes when we're scaling up a data analysis, we want to start accessing our data in a more programmatic way, and icepyx is a tool that helps enable that. But before I dive in, I always like to introduce myself a little bit more. In part because I am now an open source software developer and maintainer, but that's not the hat I've always had on. My background and training are as a glaciologist. In particular, I looked at icebergs and ice-ocean interactions, so that that boundary zone between where glaciers and ice sheets meet the ocean. And I still do some of that work. That's really what drives my interest and motivation in working with creating scientific software, and in particular, open source software. I'm also an open science advocate and educator. I work both with the University of Washington on their Hack Weeks, as well as in a number of other forums to help other researchers build their open science and collaboration skills. And so with that, I'll dive into icepyx. What is icepyx? icepyx is an ICESat-2, and I have a little plus sign here, data tool. It currently works for ICESat-2, but it has also been explored for working with certain eccentricities of JEDI datasets, and could theoretically be extended to just about any HDF5 dataset. And we do also have a module that enables you to get data for multiple from multiple different sensors. It's currently implemented for getting Argo float data, which are floats throughout the ocean, but it could easily be extended to any other data set that you wanted to bring. But what is icepyx? icepyx is both a software library, it's written in Python, as well as a community, and it's a community that includes ICESat-2 data managers, developers, users, researchers, all of you, all of us, many, many folks coming together to really thinking about how we can build these tools and collaborate better to really scale our science and use cases. And so that community piece is really critical when we think about where icepyx came from. I like to share its origin story. As I mentioned, I work with the University of Washington on hosting Hack Weeks, but I haven't always just hosted, helped run these events. I have attended them. And it was during the very first ICESat-2 Hack Week in 2019. It was about 6 months after the satellite had launched. And the Hack Week model, it's a week-long in-person event where we bring together folks to work on different projects that are of interest to them. Usually it relates to folks' research, but work on them in a collaborative setting and with the help of the experts in the room. So Mike was talking about all the different folks who contribute to producing the ICESat-2 data sets. So put them in the room with the folks using the data and talk about both the successes and the challenges that we're having. And in this very first one, there were definitely some challenges with getting the data sets. It was a recently launched satellite, very big, very complex data sets. And icepyx came about as partway through the week, a couple of the other folks in the room and I were observing, like, wow, everybody in here is doing a great job of sharing their code, helping each other to get the data and work with it. But was all kind of happening in the way that these things do in person, where people were sharing code via flash drives or sending an email or having a conversation, or all of these great ways to share information that are much harder to do when we've all gone back to our research institutions, or companies or jobs or wherever it is that we typically do our work. And so icepyx began as a way to build community, build skills in contributing code to a collective code base. It's not a skill that many of us have had training in if we have been trained in a particular discipline, or as a domain scientist. And so icepyx began as a way to both have that shared technical toolkit, but also as a way to come together and build those tools together. And from there, it has grown into a critical community tool. As you can see here in these two figures, there have been at times more than 80% of the ICESat-2 data downloads in a given month from the NSIDC, which is where the ICESat-2 data, the data center where ICESat-2 data lives. More than 80% of them have been conducted using icepyx. And then the top right metric chart is showing in the past year, essentially, I'll say where the data is stored and how it is accessed as far as the data management side of things is concerned, changed from an on-premise server to one that was in the cloud called Harmony. And so our metrics switched from one space to the other, but you can see that even in that last year, icepyx has continued being a very important space for folks getting data. And this is a technical thing, but I think socially it's also been, again, that community piece has also been really important. And this really struck home for me as someone who helped lead the start of this library when a fellow professor said that they were able to bring on a master's student to work with ICESat-2 data because they wouldn't need to take an entire year of their graduate studies just to learn how to access the data. To me, that was a really powerful moment for showing how critical it is that we build these tools and access pathways and community along with the satellite missions themselves. I've also heard from software developers that it can be a really great access pathway if they've been tasked with working with a researcher on a project to get to know some of the ICESat-2 datasets in a more technical way without being completely overwhelmed by the wealth of information out there, and really diving in on what it is that they need to know to work with this. And I'll plug this later as well. Something that we talk a lot about, something we've talked about in putting together these presentations is the criticality of citing both the data itself. So if you use ATL13 or any ICESat-2 product, NSIDC makes it really easy for you to cite that data. And similarly, citing the software tools that you're using, whether that's icepyx or any of the other great libraries and tools out there. It's a really valuable way for letting us know as the folks building those tools which ones you're finding most useful. And so that just really points to how critical it is for icepyx that we have both these technical capabilities, but are also making sure that we're supporting all user types. And that means that we want to make it easy, again, for that first year grad student who might just be learning how to use Python and what a satellite is, and what ICESat-2 is, to get those 6 beans of data and start doing science with it, all the way to the person who is developing the next set of algorithms, or making it a lot easier for folks to get data. And so again, just plugging that community piece, one of the spaces that icepyx has been able to be really active is in the University of Washington has run several ICESat-2 focused hack weeks supported by the mission with the goals of bringing together all of the folks using the various ICESat-2 datasets and working on those. And I've been honored to be able to help co-lead most of those events. And all of that said, if you've been to all of these tutorials or all of these webinars in the series so far, you might also be wondering, well, when and why should I use icepyx versus one of the other tools that's been talked about or showcased, whether that's OpenAltimetry, slide rule, Earth access, and many others. And I just wanted to, I guess, acknowledge on behalf of those of us who develop these tools that it can be a very confusing landscape. And part of that is because of the history of the development of the tools, which is that the tools developed right alongside the data. The technology has changed so quickly that there's no way anyone, when they were designing the mission and the data sets themselves, could have predicted what computational tools would have been available to work with it. And so if you draw a diagram of how icepyx relates to some of these other data sets and tools, it kind of looks like icepyx is in the center, which is not fundamentally true. We would expect that perhaps ICESat-2 is in the middle, or even a more general tool like Earth access is in the middle. And so I wanted to acknowledge that because it's something that we as a developer community are actively working on. And so if there are things that you as a user or as a developer see that you're saying, oh, it would be really clear if the access pathway for me to get and use data went this way, we always love to hear that kind of feedback because it's easy for us to know all of the ins and outs of when you should use which tool and why. But making that clear to everyone else is something we're actively working on. And here's a sort of hypothetical of the way that we're thinking about how this ecosystem of tools and tooling could look in the future, and how icepyx, ICESat-2 data, slide rule, Earth access, and all of these tools might interact, and that would all happen in perhaps a space like CryoCloud, which is a managed Jupyter hub that is built and managed by 2I2C. With that, I'm going to dive specifically into icepyx as a software. Hopefully you can have a chance to watch some of the other webinars to learn more about these other tools. But I'm going to dive specifically into icepyx, and then we're going to move into a little bit of a demo to show you how to work with icepyx. So what features does icepyx have? Like many software libraries, it has a full documentation page. It's got ICESat-2 resources. It has the ability for you to query data, so search for that data. You can submit that data as a request and get the data subset spatially and temporally, which is something we're going to do in our demo. You can visualize where you've requested to get data. I mentioned that quest module earlier to get data from multiple different sensors using the same spatial and temporal inputs, so you don't have to keep re-entering that information. And under the hood, icepyx uses the Earth access library for handling authentication, because in order to get data from NASA data, you need to have an Earthdata login, which is free and easy to get, but it is required for you to get the data. And as I mentioned initially, one of the big motivations programmatically for icepyx was that we took some of the early scripts that were being used to programmatically get data. They were about 50 lines long, and we turned them into 3 lines of code. So the typical user didn't need to learn all of these really detailed things about how to send requests over the web to get back, simply to find out what data was available for the area they were interested in. Some more fun features of icepyx: in addition to getting search and access data, we can also read the data in. Currently, this is best done locally, and then the data is read into what's called an X-ray dataset. But we are currently in the process of revamping that data read-in module based on a whole bunch of speed testing to improve the speed of the data read-in, but also to shift it so that that data read-in works equally well or as close to equally well as is technologically possible in the cloud as well as locally, which means you would be able to avoid downloading all of the data that you need and could just access it directly in the cloud. It also means your workflow would be portable between a local setup where you might have access to data and the cloud-based workflow. And last but not least, I do want to mention, and I'll showcase this a little bit in the demo, the availability of this nested variable management. A given data granule for ICESat-2 can have over 200 data variables, and they're highly nested, and it can make getting quote-unquote simple pieces of data like latitude, longitude, and height very complicated because you have to look in multiple places. Last but not least, we have lots of ongoing work. As I said, we're working on that cloud-optimized data read-in. We're thinking about how we can streamline access to ICESat-2 datasets across the entire ecosystem. icepyx itself is participating in the CSCCE's Berdaro program to think about sustainability and governance. And we would love to hear from you about what features and functionality you would find most helpful in your workflows. So hopefully by now I've convinced you that you should use icepyx. If not, we want to replug that it's a great community to be a part of and learn new skills as well as a technical tool. It knows some things about ICESat-2 data, which can be really convenient because ICESat-2 data otherwise has a really steep learning curve for starting to access and work with the data. It also allows you to work on the cloud and locally. It defaults to the latest version, but enables you to get any version of the data that is available at NSIDC simply by setting the version. And it's easy to install and helps make your science reproducible, which can be useful for your future self as well as for sharing with colleagues. I won't belabor this too long, but I know we're already past the top of the hour, but I wanted to make sure everyone knows that they're more than welcome to get involved, reach out to me, or better yet, post on our GitHub page. And remember that contributions and collaboration in this space aren't just thinking about the code. They can be asking questions, they can be telling us about issues that you've found, and also just letting us know what you like about a tool or what you wish it could do. And so with that, I'm going to jump over to a demo on how to use icepyx to access and plot ATL13 data. So, okay. So, I think Jennifer's going to post the link to this. If not, it'll be available afterwards. And hopefully, potentially, this demo can be moved into, it's currently in the icepyx repository on GitHub, but I'm hoping that we can move it into a shared tutorial guide that is being put together by by many folks across the ICESat-2 ecosystem who have produced and or maintained tutorials. We're collecting them all into a single location to help make it easier for users to navigate.
Maybe 1 plus larger if you're able. Yeah, that's great. That looks good.
Yeah.
Does it make it too big for you? It looks good here.
I was gonna say that's okay for me. Thank you, Michaela. Okay, so I won't spend much time on the start of this. I'm not going to go through the details of Jupyter notebooks or how to run them. Happy to direct folks towards other resources if that is something they are interested in. I do also want to note, if you do try to run this notebook on your own, that it currently uses the development branch of icepyx, which has a bug fix that was just put through this past weekend. And I have been sick, so I haven't been able to help shepherd a release through. That being said, we're going to look at a use case of Lake Mead, and I'm running these cells quickly so that going to come back to them so that I can get the data order itself going while I'm talking. So here we've just input our spatial extent, which is a bounding box, lower left, and then upper right, some dates. So more or less the entire duration of the ICESat-2 satellite. And then we're going to look at a specific track that happens to fall over Lake Mead. So here I've created this data object, which is querying the data. We're looking at the ATL13 dataset and the spatial extent, all the information that we just added up there. And if we want to make sure we've entered everything correctly, we can run this handy function to visualize our spatial extent, and that provides an interactive map. We can see the bounding box that is our region of interest, and that's an interactive map that we can zoom in and out on so we can see where Lake Mead is and where our bounding box is in the context of the regional topography and also context of the US. So here we've just said, okay, can you let me know what granules or files are available that have data in that area? So we've just printed a list of those there. And then what we're going to do is we're going to go ahead and order that data from NSIDC. And as I mentioned, you're required to log in to access this data. This login happens behind the scenes in icepyx using the Earth Access Library. But if you have not stored your credentials locally for this to work, it will prompt you for your username and password. So if you don't have that set up, that's fine. It'll let you interact with it directly to get that data. And then, as I said, I placed this order a couple seconds ago so that it would go through. And now we're in the process of downloading all of those granules to my machine. Once we have done that, we can go ahead, create what's called a reader object. I discovered that the native read function is not working for ATL13. As of the latest version of icepyx, it might also have something to do with the latest version of the data, which, as Mike said, was released late this summer. So it's possible we just didn't pick up on a change yet. And I discovered this recently, so didn't have a chance to dive in yet and fully determine what the cause of that is. But you can expect a fix for that sometime soon. And what you see here is we've just gone ahead and created this read object by directing icepyx to where the data lives on my system. And it has created this list of files. I didn't have to do any fancy rejects or anything in order to get it to find the data, which could be really handy if you're trying to if you have a lot of data files on your computer. And so, as I said, what we want to do is we want to get a couple of different variables to read into plot. And if some of you have seen other tutorials, sometimes what they do is they have this long manual list of all of these different variables and paths to them because you have to get the variables from within each of the 6 beams. icepyx has a cool function, variables management function, that allows me to just supply the names of the variables and say that I would like to add those. And then it creates this dictionary for me of all of the paths that I need to use to get to those various variables. And so I'm going to use this information in this function that I have created in order to load all of that data. And we have now loaded all of that data into a pandas data set. And so we can see for every single point, we have the segment latitude, longitude, the height, and I've also added a date field so that we can group our measurements by date. From there, we're going to make sure we add some geospatial information and then go ahead and plot. I'm using GeoViews to create these plots. They'll take a second because it's aggregating all of the data. But what we're going to get here is a background tile, again, showing the region, and then the photons, or not photons, sorry, the data points of those heights that are available over that lake, Lake Mead, for each of the dates. And the dates will have a drop-down bar, and I can scroll through each of those dates once this finishes running. And I'll go ahead and start this one as well, which is an alternative way to view the data on a map. So there's two different ways, one using GeoViews, the other one is using built-in functionality in Pandas. This one we have, let's see, say there should be a scroll bar so we can see our Lake Mead, and this is an interactive map, so we can zoom in and out of this map. Where we go? It's taking a moment because I have the next one running as well. And it's hard to see with this font zoomed in so much, but if I were to zoom out a little bit, what we would see here is this drop down. Oh, go back to this one. You can see there's this drop down with the dates of all of those different granules. So we can look at a couple of different dates and we can scroll through. Apparently that one didn't work. Might just be taking a moment to, I know what's happening. I was gonna say it's in the other part of the lake that you can't see because we're so zoomed in. There we go. So we can see for each of these dates, we can see what data is available, and we can see what the elevation is of the individual points for that date. As an alternative, here, let's see, I can zoom out a little bit. Using that built-in functionality from GeoPandas, I have plotted all of the dates. So if we wanted to say, dive in and say, oh, let's compare these two tracks that are right next to each other across two different dates, we could do that more easily. So we can see where and when there is data for all of these different regions of the lake. And with that, I will hand things back to Jennifer for questions.
Okay, thank you, Jessica, and thanks to everybody. At this point, what I'm going to do is I'm going to open up the final optional polling questions and jump directly into the Q&A session. All right, so let me open up the poll, and that will be running in the background for like 30 minutes or so. So the first question I have, and I will also check the chat because I know some questions were asked there as well. The first question is, and I think this is for Mike, so Dr. Jasinski, the question is orthometric height the same as height above sea level? You'll have to unmute yourself. All panelists have been remuted. Let me know if you need me to.
Yes and no. The orthometric height is the height of the Earth's surface above the geoid, where the geoid is this sort of gnarly integration of curves representing the gravity of the Earth. Okay. I just want to answer that and let you know it takes about 20 times to hear this before it starts to stick. Okay. It's not that easy. So right now, the orthometric height is the EGM 2008 datum. Okay, the Earth Gravity Model 2008. It is technically the height above the ellipsoid of the Earth. I'm sure that cleared it up.
Right. Oh,
Go-
sorry.
Go to your I'm being a little sarcastic there because it's a difficult concept. It was a difficult concept for me because there's a geodetic height, there's an orthometric height, and the Goddard, the ICESat-2 project publishes both of those heights for some of the parameters, and specifically all the height of parameters associated with the inland water product are published with both the orthometric height and the ellipsoidal height. Okay. So
Right.
when you
sorry.
when you go out and measure the water surface, that height is the orthometric height. Okay, the height above the ellipsoid.
Okay, thank you, Dr. Jasinski. So our next question is, this data set will this data set provide wind speed over inland lakes or just provide the backscatter? Give me just 1 second. The chat is,
Okay.
apologize. Let me get back to it. The chat always obscures the view of the. Okay, will this data set provide wind speed over inland lakes or just provide the backscatter? What is the spatial resolution of this data set?
The spatial resolution of the data set is at the short segment length. Okay. It's for the along track product, the short segment length is the length it took to gather 100 signal photons. So if you're on a sort of a hazy day, you're going to have to go a little further, maybe 200 or 300 meters before you get 100 signal photons, which are classified in the ATL13 product. Okay. On a bright sunny day, you get a much shorter distance down to about 25 meters. You can get 100 photons. If you go any more than that, the instrument freaks out because it has too many photons coming back to the surface. Okay, so the length, so your pixel, your spot is variable. Okay, and that's already factored into the short segment length. Okay, now let's see. The second part of the question was wind speed. So we have an empirical formula for the wind speed. It's based on the standard deviation of the water surface photons. In the ATL13 product, we assume that the variability in the water surface elevation falls within a Gaussian distribution. It's not exactly right because the swells and the crests are not perfectly Gaussian, but there's so much other noise going on in the distribution of the photons. It was easiest to assume a Gaussian distribution. Based on that Gaussian distribution and the distribution used by NOAA in their buoys, we assumed, I think it's the wind speed was based on 4 times the standard deviation of that distribution. I'm not exactly sure what the factor was in there, but that's how we estimated the wind speed. If you go to the ATBD, so that's the ATBD for ATL13, you can download that easily from NSIDC, and I'm not sure exactly what chapter or page that is on. It's been a long time since I looked at that particular calculation, but it's basically embedded in chapter 4. It's a real technical chapter in the ATBD. You can get that answer out of there. Okay, that's not on the tip of my tongue. It's a long time since I looked at that, but that's how it is. The wind speed is computed based on the standard deviation of the water surface. So that that, took that amount of time, based on a sustained wind to, you know, develop waves of that height. So, I mean, I think NOAA uses that. There's more technical and better ways of defining that, but that's what we used at that time, and we haven't had time we weren't given time to change it.
Okay, thank you, Mike. The next question is, can you estimate Q from these data? And I'm not sure if there's part of this question missing or
Skew?
Q. Can you estimate Q from these data?
What is
Dis-
the
Discharge or flow rate, I'm thinking.
is that what the question is?
Well, the question is not worded in that way. So if okay, there we go. Stream discharge.
Okay. Well, what do you need for discharge? You need, there's various levels what you need. I mean, the very, very, if you're running a real hardcore hydrodynamic model, you'd want the cross section of the river, and you'd want the slope of the river, you want the width of the river, excuse me, and from that you can use a hydrodynamic model to estimate the discharge. We don't do that. Okay, there are other folks out there who run large scale global, like almost global models, and they make estimates of they can use that information. I mean, if you can get the slope of the river, then you can estimate, fairly good Q depending on what type of flow. Is it normal flow? Is it, a dynamic flow? Was it steady state? So those kind of issues come into play. So do I think you could do it? I think you could do it. Be creative and figure out a way, how to apply that slope. You don't have a lot of slopes to work with, but that is often a very important parameter in estimating the discharge is the slope of the water surface. Why is that? Because you can estimate the slope as it's similar. It depends how big you want your air. I'll just end it there. But take a look at what they use for like the HEC-RAS models, the National Weather Service River Forecast System. Some of the models, we have a model in our lab, HIMAP by Gusto Gaterano. He has developed a global model. Well, he doesn't get the cross section for every part of the river base, so you can go and see what he does, and maybe you can get an estimate there.
Okay, thank you, Mike. The next question, I'm going to take one from the chat, and then we do have another question in the Q&A that I want to get to. So the question is, excuse me just one moment, I'm just, will there be an ICESat-3 or the next version of the satellite?
Will there be what?
Will there be an ICESat-3 or the next version of the satellite?
Do you mean a new satellite?
Yes. Will there be a follow-on? I'm guessing is what the question is. Will there be an ICESat-3 to follow after ICESat-2?
To my knowledge, there is no plan to have an ICESat-3. Now, there are other missions that are, trying to, arise here. There's a surface topography, the vegetation mission, STV, that's sort of in the incubation period. There's another satellite, which, it hasn't been defined, but there's already a group working on it across the agencies and across, academia, called PBL, the Planetary Boundary Layer Mission. And folks have concepts on what that might look like, but none of them have reached the stage of this is the concept we're going to go with. There's still a lot of work to be done, a lot of tests to be done, a lot of studies to be done, simulations. Are you going to put up a single satellite? Are you going to put up a constellation of satellites? What sensors, what frequencies would you be using? Right, that's the stage of it right there. So all that stuff takes a long time to iron out. It's a beautiful process, but involves a lot of, really smart people and good concepts, designs, different locations, Depends on what the Europeans are doing at the same time. Maybe they have a similar mission coming forward. So all that sort of gets coordinated. And with the budget the way it is, I'm not sure where Earth Science is right now as far as new missions. But it's a great question.
Okay, thank you, Mike. The next question is, how do the orbits progress? For example, I saw on the large lake images it had multiple approximate north-south passes. Are these passes incrementally, for example, rapid coverage of the lake, or non-incrementally, excuse me, reducing the period for repeat visits to a large lake?
Yes, that's a really insightful question. And I don't have the final, what the answer is today, but ICESat, runs an orbit and on a 31-day repeat cycle. And I think it may be 91 days within a 31-day subcycle. But so it progresses, around the globe, and you don't get back to the same spot until like 91 days. Now, to add complexity to this, the ICESat, because of the vegetation requirement on ICESat, that is, they wanted to map all the global forests. The exact repeat of ICESat only occurs in the polar regions. Okay, so it starts like in mid Alaska, and and really you're about like 70 degrees north, 75 degrees north, and you get the ice caps, you get the sea ice. That's what drove the mission. That's what defined the orbits of the mission. Now to get the orbits converge right around the poles, 92 degrees. They practically go over the North Pole and the South Pole directly. But so that if you took let's say 31 days to cover the Earth, then the satellite shifts a little bit where it's designed to automatically just take that progressive orbit, and you get another set in the the 32nd day and the 33rd day. I think it's so it takes it's not exactly repeat, but it suits the needs of like getting a full distribution of the ice, and the water takes advantage of it too. So I mean that's the answer. It's sort of a complicated answer, but no, it doesn't exactly repeat. However, there used to be, and I'm not sure if they offer this capability, but you used to be able to say, I got this water body in, somewhere in Africa or, in Europe, and I want to hit that same spot. You used to be able to say, you could make a request, and if nobody has priority over you, you used to be able to go and say, okay, will you give me the right orbits and the tracks? We can off point the satellite to do that. In fact, that's what the satellite does. It slightly off points in order to get like a spatial coverage. So if the orbits were separated by, let's say, 500 kilometers or something, or 1,000 kilometers, it has, in order to do the vegetation cover, it off points slightly left on one full set of orbits, and then slightly right on another set of orbits. Then they split the difference again, and they do that type of progressive coverage. But it takes a long time to get back to the original.
Okay, thank you, Mike. With that, we actually have completed our Q&A session, but what I encourage and I know we didn't get to all of the questions. I see a couple of more questions in the Q&A. So at this point, what I would recommend is if our panelists can stay on the line and type a response to the remaining couple of questions in the Q&A, that would be wonderful. I'd like to thank all of our panelists this afternoon and thank our speakers for their time and for their content, and thank all of you for joining us this afternoon. What I will do is I'll log off from the audio component, but I will leave the virtual meeting space open to afford an opportunity to everyone to, fill out the optional polls if you're interested. And certainly if you panelists, if you have a moment to respond to a couple more of these questions, that'd be great. Otherwise, our speakers can also follow up with you offline. I will send them the Q&A log. So thanks so much to all of you. And we hope to see you at an upcoming webinar. With that, I'll log off from the audio and leave the virtual meeting space open. Thanks so much, everybody.
Thank you for attending.
Have a wonderful afternoon. Thanks, everybody.